Hey guys, welcome to our first lecture on vectors. Let's first define what a vector is. I'll write it out and then I'll describe it. All right, so I've described it or defined it as vectors are quantities that have both magnitude and direction. Let's talk about what quantities might be involved. We have displacement. Displacement is a quantity similar to what you guys saw in that treasure hunt. I gave you guys instructions like go north 7 miles. That's a displacement quantity that gives us a specific vector to head on. The other two important ones for this unit will be velocity and acceleration. And we'll talk about those more in depth. But when I say quantities, I'm referring to these physics values, and specifically these physics values that have the vector behavior of having both a magnitude and a direction. But I keep using magnitude and direction without defining those. So let's go to magnitude and describe what we mean by magnitude. Magnitudes are always going to be really recognizable because they're the things that have value when we describe a vector. If you see a number or a variable that represents a number, that must be the magnitude. A vector has to have magnitude and direction, but there's a different idea, something called a scalar. Scalars are things that are only magnitude. And so I'm going to give you guys some pirate instructions that involve only scalars instead of giving you guys the displacement vectors that had direction as well. So here's just the scalar versions. This is magnitude only. And let's say I said, go 5 miles, then 10 miles. Oh, great. Okay, thanks. 5 miles, then 10 miles. Is that 5 miles east, 5 miles north, 5 miles south, 5 miles southwest, whatever? It doesn't say because I only gave you the magnitude information. And then it says then 10 miles, but it doesn't say go 5 miles and then 10 more in the same direction. We have even more confusion here because that could be 5, then 10, 15, or it could be 5, then flip around and go back 10. So we actually went 5 total in the opposite direction of where we started. There's a lot of confusion here if we don't also give that direction information. So I've given you guys the distances here. That's the scalar version of the displacement. But you can't you can't find the treasure. You can't use this vector because it's incomplete. So in order to complete this, direction needs a little bit less discussion, but let me do something where I give you treasure hunt information, but only direction. I didn't give you magnitudes at all. So I said something like go southwest, then north. Great, thank you. Southwest, how far? North, how far? Not very useful. The displacement vectors, knowing from where you started, where to end up and like get to that location requires a vector that gives us the magnitude, which is how far to go, but also the direction, which way to go. So if I combined these two things together, it starts looking like what you guys were dealing with in your activity day, where you knew how far to go and in what direction. And as you follow those vectors, you eventually got to where you needed to go. So that's the definition of a vector. Just to repeat it one more time, it's a quantity with both magnitude and direction. But now let's go to some of the ways that we can represent vectors. One way to represent it is, of course, just to write it out. We can say 5 miles southwest, then 10 miles north. Embedding into that both the magnitude and direction gives you everything that you need to know. But there are some shorthands that are a little bit faster than having to write out entire sentences every time. So one of the shorthands it just involves using graphs. You can put all of the information for vectors, for the most part, into coordinate planes. Let's change colors. I've been blue for a while. One vector that I could do is I could do a vector that looked something like, let's try something a little simpler first. Let's just do this vector here. Let's do a vector that goes that way. This is a very simple vector, but you already know how long it is and what direction it is because I drew that arrow. We now know that it's this long, and we know it's going along the x-axis. So if I wrote that out, or if I was describing it to somebody, I would say this is a vector that is 5 units long. Units is in units of the graph. 5 units to the positive x direction. That tells me that I'm going this way and not that way because I'm going in the positive x direction. You could do a different vector. We could go, let's do this one. This is pretty easy. We could be going that direction. And this one we could describe it as 2 units to the negative y direction. If this is the positive y direction, this is heading in the negative direction. So that's one way we could write it. Alternately, though, we could also write that as negative 2 units to the positive y direction. And we saw this in the treasure hunt today. If I'm going if I'm going negative y, that means I'm going this way. 2 units, okay, that gets me to here. But if I did the other option, I'm going this way, but I have to go negative 2 units. Then I'd go there and then there. Oh, there should be an S there. Whew, saved it. So those are how we can describe vectors, both graphically and repeating it with some of the long form words. But vectors, unfortunately, don't always lie right along the coordinate plane. So sometimes we end up with vectors that are going this direction. And once we have that, we have to start using some more specific language where we have to say things like, okay, I know it's going in that direction. It looks like it's actually eyeballing it, I don't know, 36.8 degrees, roughly, 36.81, if I had to really feel like I nailed that. So I know the direction of the vector, but 36.81 degrees actually isn't enough. I actually need to say something like counterclockwise from the positive x direction. Now you know where I started drawing my angle from, you know which direction I went in. I went counterclockwise instead of clockwise, and you know how far I went. So I gave you all of my direction information, and then for the length of my vector, we'd have to measure that. There's some other tools here that we'll talk about. I happen to know for a fact that I drew one that was exactly 5 units long. If you don't believe me, print off this sheet, make yourself a meter stick, or make yourself a measuring thing, and you'll find out that that's pretty darn close to 5 units long. So with that in there, those are ways to describe vectors, but I have one more way to show vectors that I want to talk about in brief, and we'll use it throughout the school year. So first thing, this is how you note a vector. I'm saying quantity A, so we'll say that one's A. This is a vector A, and I put this arrow above it to say, okay, this isn't just any variable, this is a specific variable representing a vector. So you can do it with two arrows or with one. I usually do it with one. And then that shows that it's a vector. But then to describe it in a much more compact way than having to write 5 units, 38 or 36.81 degrees counterclockwise from the x direction, which would take us a lot of time. We can describe it by describing how far over it goes in the x direction. That's 1, 2, 3, 4. That would be 4 units in the x direction, and how far up it goes in the y direction. 1, 2, 3. Okay, 4 and 3, that's not good enough. A does not equal 43. So what I also have to describe are what's called unit vectors. There's a vector that all physicists agree called I hat that is always 1 unit in the positive x direction. So if I said it's 4 I hat, that tells me it's this times 4, so that far over in the x direction. And then another one that physicists have agreed upon is the j hat vector, which is always a 1 unit long vector in the positive y direction. So since it's 3j, it's going to go up 1, 2, 3. And you can see that combination of information right there, 4I hat plus 3j hat, gives me this vector, because this is a vector that goes 1, 2, 3, 4, and then 1, 2, 3 up. So this is called IJK notation, or unit vector notation, or probably some other names that I'm not listing right now. But it is a very useful tool that also helps us start practicing the way we really want to look at our diagonal vectors, which is to see that all vectors along the diagonal actually exist as a combination of x components, that's x pieces, and y components. And breaking them up into x and y components is a very useful tool for solving a lot of problems. But right now we've talked about everything we need to know about what a vector is. So our next video will be about how to use vector mathematics, which is combining vectors in different ways. So we're going to take a break, and then I'll launch the next video. Thanks.